So far in this course, we've calculated a mean, a median, standard deviation with Excel. We've been asked to choose a winner, without giving a specific set of criteria, so that allows students to have some freedom for what decides a winner. Then we started getting into Z-scores. We started talking about something called the central limit theorem. So this video is trying to tie all those ideas together and just let you know why we do these things in the first place. Stats is my favorite part, like introductory statistics is my favorite thing to teach. So without going into too much detail, let me just do a quick example of what a Z-score can do for us and what it really means. So a biologist goes out in the wild and it's looking for species that are going to be extinct. And one number it's decided that's really important for these species is the weight. One biologist finds a creature that weighs from species A, finds another creature weighs, let's say, 72.5 pounds from species B. Okay, two different species. Biologist finds these two creatures, and the biologist has an idea of how much these creatures usually weigh. And the biologist knows they're above average. That means they've been finding food, they're likely to reproduce, so this is a good thing. Okay, so which one is the biologist more excited about? The 4.2 pound species and the 72.5 pound species? Obviously, they're totally different creatures, right? So it's not fair to just say species B. Mean deviation of 1 pound, and species B has a mean 60.5 pounds and a standard deviation of 10 pounds. So which one excites the biologist more? Well, they can get down on one knee, calculate a Z-score like students in the class are typically good at calculating. Here's the Z-score for the first one. Here's the Z-score for the second one. It's a 72.5. The individual is 72.5 pounds. The population mean is 60.5 and the standard deviation is 10. So if we crunch those out, when I do videos I have a hard time with mental arithmetic. I'm pretty sure that's 0.7, and then this one, I'm pretty sure that's, no, that's not 2. Is that 2? Calculate. 725 is directed by 605, 5 by 10. That's 12. What did I do? Oh, 0.5. When I do videos, I get all flustered and I miss little things. And divide that by 10. Okay, that makes more sense. So 1.2. Okay, so now the biologist has something to quantify their excitement. The second creature has a Z-score of 1.2. That means they're above average compared to the other creature. So that's what a Z-score can do for us. Okay, that's just a Z-score. We're not talking about probability yet. Okay, probability comes in when we assume that the variable is normally distributed, and often that's a dangerous assumption. A normal distribution is an unfortunate word. I like the Gaussian distribution because normal distribution doesn't just mean a variable that you see all the time. Okay, a normal distribution is something that makes this bell-shaped curve. It's probably the most common thing that we see out there because the normal distribution is centered around the population mean. Okay, and when you convert a number to a z-score, that means z equals 0 is the center, by the way. Okay, so what you look up when you use the table or when you use a computer function, when you're talking about a z-score and calculating a probability, that's using the assumption that it's normally distributed. Okay, so that's something you would want to verify first before trying to interpret a probability. So like in our discussion board for like weeks 3 and week 4, let's say we got a z-score of 1.3 for a species. Okay, just throwing a random z-score out there. If it's normally distributed, that means, when we look up this value, I don't know off the top of my head what 1.3 is in the table. But if we look up this value and we get a probability, actually, I should do it this way. The table gives you left tail probabilities. By default, you can use computer functions to automatically give you the right tail, but I'm just making up, I don't know exactly what this is in the table. Let's say it's 0.9153. That means 91.53% of the population has a value that's less than the one that we just tested. The species would have a smaller weight. So this species is better than roughly 92% of the population. Okay, but to get the right-tailed value, that's just simple arithmetic because there's 100% of the species we're dealing with. If 92% was to the left, then 8% is to the right. Okay, so that's what we do with those probabilities. We're thinking about this individual aircraft compared to all the other types of aircraft. So the KC-135, what was its cost? Well, we can take that cost and we can subtract it by the mean cost and then divide by the standard deviation cost. Turn it into a z-score. And then the probability tells us the probability that we randomly select another plane and it's bigger or smaller than this particular plane. So let's say for your discussion board, actually I have this, a student sent me this, their work on the discussion board. Things are looking good, you know, they've highlighted, it's really easy to see what they're doing. They're looking at Kadena for the bomber B-52. It's got a score of 6.8. We can convert that to a z-score, which it looks like they did successfully. 6.8 minus 8.9 divided by 4.16. Yeah, that looks to be about negative 0.50, so that looks good. So what that means is that it's a below average cost, okay, because the z-score is negative. And what the probability means is that if B-52 bomber costs are normally distributed, if they meet this curve, then there is a roughly 31% chance that any other randomly selected bomber would have a lower cost than this B-52 bomber. So the probability gives us an idea of where it stands compared to all the other values, just like a z-score does, okay? But it puts it in more real-world terms. So if you were to get a probability of like 0.67, let's say something higher, 0.98, the probability of being less than the z-score is 0.98, that means there's a 98% chance that any other B-52 bomber would be less than your current B-52 bomber. Okay, I hope that helps with what a z-score means and what the probability represents. It's assuming, you know, if you can safely assume that it's normally distributed, then the probability tells us, sorry that this is so off-centered, the probability tells us the chance that you get that you were to pick any one of the B-52 bombers and it would be just as low or just as high as this one. Okay. Let's check out what else we have going on in this week's discussion board. So we made a histogram. So this looks okay. If you, let's see, if you are in StatDisk, there should be a function where you can change the number of bins. It can be hard to find though, so if needed I can make a video for that. I'd have to poke around too. StatDisk, I usually use R when I do statistics work, but for this course StatDisk is easier. R gets way too complicated sometimes. So usually what we like to see in a histogram is more than 4 or 5 of these bins. There's 3 bins here, because if we do that, then maybe we can get an idea of its shape. Okay, maybe if we were to break this up into several smaller bins, then we'd be able to see that it looked normally distributed except for this one outlier. Okay, but if we were to go off this histogram alone, does not seem to make a bell-shaped curve, right? Bell-shaped curve is supposed to be in the center there. Most of the values are to the left, so there's an outlier that's pulling it away. And the box plot, you know, it indicates this as well. It doesn't make the bell-shaped curve. It's not symmetric, right? It's not all clustered around the center with a few to the left and a few to the right. And this QQ plot, this looks like it's done correctly, so that's great here. The QQ plot is plotting z-scores, okay? So it's converting every number to its z-score. If it was perfectly normally distributed, then the x values and the z-scores should all fit on this dotted line. Okay? Since this doesn't fit a perfect straight dotted line, primarily because of that outlier, that means it's not normally distributed. Because if it was in a QQ plot, it would land in this line going up. So this indicates it is not normally distributed. So that means the probability that we got here has little interpretive value. Okay? Yeah, we got a probability from the table, but the table assumes that it's normally distributed. So 0.3085. That's a number that isn't actually going to tell us the truth because our underlying distribution was not normally distributed. So that would be a good thing to note in a discussion board post. Let me see if there's anything else here to check. Mean and the median are there. Confidence intervals. I don't think we've got the confidence intervals yet in this at this point in the course. I'll make some videos on how to make those in StatDisk. I guess one last thing. I think this discussion board asked about the central limit theorem. Hopefully this isn't all too much in one video, but the central limit theorem is specifically talking about this, the mean. Okay, the central limit theorem says this thing here is going to make a bell-shaped curve if you were to graph a bunch of them, if you have a big enough sample size. Okay, so if you were to make a whole bunch of sample means, if you go out and gather one sample, calculate the mean, then gather another sample, then calculate the mean, and then do that again and again and again, and you put them all in a data set, make a column of numbers, put all the means here, type them all in, and then make a histogram, it's going to make an approximate bell-shaped curve, assuming you've got enough of them. Okay, so the central limit theorem says if you get enough samples, if the sample size is large enough, then the mean is normally distributed. So that solves a lot of problems for us. The data set that we were looking at for this discussion board, the QQ plot indicated that it is not normally distributed, right? So the z-score has little interpretive value. And so that means we can't do a lot of cool stuff in statistics. But the mean, which is, it's calculated from the data, the mean is normally distributed if you get enough sample size. So if you go out and go collect enough numbers. And that's great because that assumption lets us use those z-scores again. Or more often it means we get to use a t-value, okay? Okay, I think that's probably enough for one video. If there's still questions on the content we're working on, please let me know. I'll be glad to help out.